So what do we do today? There are today. Let me do everything in sequence. We do have reserved Friday the room across the corridor, EML 183, for additional group meeting. So whatever we decided for, and we can do literature review meetings on Fridays. There is effort to complete manuscripts based on Sanibel by the end of April, and it is a lot of load for editing, like we did last time. So even if some of the authors didn't include themselves into the loop, if we do it energetically, they finally realize how important it is. And today is the last chance to do accent on figures. Next time, I don't know, well, we will decide at the end of the meeting, but next Tuesday is the spring break. Please lift your hands if you plan to travel, or if you agree. Is there a spring break next week?
Yes.
Yes? Do you stay in Fargo or you travel elsewhere? Or you haven't decided yet?
I haven't even thought about it.
Oh, okay. So it would be really great to have a meeting on Tuesday, but it can be doubtful because the rooms can be locked. So I will warn it and inform everyone. If it will be available, we can make a meeting when everyone presents conclusions in written forms, and we go over. If not, we will postpone everything and make last month before submission really intense. And we need to decide who will present this Friday.
Oh, we didn't reserve room yet.
I did reserve.
Which one? This?
Across this corridor.
4 p.m.?
4 p.m. Yes, 183 EML each Friday. So here are the materials for today. So it includes presentation by John. And
so for Friday meeting, I have 2 people out, right? So Jabet and Braden are out, so they definitely cannot present. And other 2 my people also have already presented.
Well, Levi, so we can listen for Levi on Friday.
Maybe if Levi would you be able to present Friday rather than today? To save time for today's meeting. Okay,
and then you will have more time for feedback.
And so what time is it on Friday?
4 Fargo time. It's 3.
Okay.
4 p.m. Fargo time.
3 p.m. your time.
So it is the same link for online. And and if Aaron wants to volunteer, well, if anyone wants to volunteer to present on Friday, it is open for a second presentation. No, we can postpone.
And again, I just want to highlight, we present just introduction. Don't try to present the whole paper, right? Because we don't have time for this. We do it really parts by parts. And for 20 minutes, it would be just focused on your introduction, right? Literature review, motivation, challenges, and overall the way how you are addressing these challenges being different from what have been already done in the field.
It is what John is going to present, just so that we will follow and ask him well-grounded questions.
Everything just for John?
No, then there are undergraduates, and hopefully some of them will come and participate. But our first point in program is John. Okay, so John, would you like to share your screen, introduce yourself, and start presenting?
Yes, I can do all of the things.
Oh, nice.
Okay. So you guys can hear me? I'm not going to be able to see you if you raise your hand, so just yell at me. If you'd like to say something, then I'll switch back so I can at least see you guys. Okay. My name is Vogel, and I think we all know each other, but just in case you don't. So there are two things about this that make me a little bit nervous. One is presenting work with authors sitting in the room. I'll do my best to at least go through the main points that I was thinking about, and then simply there's just a lot of material, even more than I thought once I started looking. I tried to keep it concise and build a logical approach. So what I'll talk about today is looking at the photocapsidation of organics or other types of reactant molecules, and to utilize cadmium and lead-based quantum dots functionalized ligands in terms of a photocatalyst for these types of reactions. It's just the introduction, and so with the outline, I just talk a little bit of motivation, and then go through some of the literature that I've been reading and looking at, and try to highlight what I think within that literature is missing currently, what understanding can we provide that no one else has, and then try to think about the methods that we're going to use to try and provide this information that could be useful to the rest of the community. So the first slide here on motivation I have listed here. Kind of like I said, we're trying to take a look at lead and cadmium chalcogenide quantum dots functionalized with either organic or metal organic ligands type of charge transfer within the system to be used for redox reactions. And so it's been known that ruthenium-based bipyridine compounds have been used electrical or electron donation type materials, but specifically we're looking for complexes that are going to facilitate hole transitions following some type of photoexcitation, and so that hole can be used in an oxidation action. And so at the top you can see one paper title, which was from last year, this quantum dots and visible light. And so why is it that this is to be able to look at these whole charge transfer events that lead to redox reactions? But one application is, of course, in conversion of solar energy to electrical or chemical energy. When you think of renewable energy field, people are always interested in how charge carriers are behaving, chemical energy like reaction, but also in other types of industries such as pharmaceuticals, like the food industry. There are retail manufacturers, people who are doing things like with perfumes and colognes, so olfactory sensing of taking these whole general complexes and using them to do some type of organic molecule conversion. And so the title at the top is talking about of alcohols into carbonyl compounds, so changing these alcohols into either some type of aldehyde or ketone. And it's also important because we want to...
Hello? We do have a question.
Yes.
So,
okay.
Before you go deep to the whatever applications and so on, you already mentioned charge transfer, right? And you also talked about photocatalytic reactions. So probably would be good to first of all explain what do you mean by photocatalysis, right? How is it different from catalysis? Okay. And second, why charge transfer really, like what the role charge transfer is really taking for such catalysis. So in other words, probably focus on the process. Like, okay. You were too short on just explaining the physics and you went deep to the applications while we really didn't get really the processes which you are trying to discuss here.
Okay, so I will now treat this.
Maybe you have it later, I don't know, but looks like.
No, that's fine.
For people who are not familiar with this topic, it might be an issue, right?
Okay, no, that's fine. I was thinking down a different path. So when we're talking about photocatalysis just versus catalysis, what we're wanting to do is we're wanting to be able to take the energy stored in a photon of light coming into the system, having some type of optical transition be induced by this photon, and study how the two carriers are relaxed non-radiatively, be pulled out of the complex itself. But this is also dependent on the type of optical transition that's induced by the photon. And so in some of the literature review, the examples of this, but we need to be considering optical transitions that occur, quantum dot itself within the functional ligand itself, but also transitions that may be induced like a metal to ligand charge transfer or ligand to metal charge transfer. And so these types of...
What is a catalysis? Like, which of the systems really doing the catalysis?
So with
and why do you need photoexcitation?
So with the photoexcitation, the generation of two charge carriers, an electron and a hole, we want some type of charge transfer to get to a surface. And in this case, we're looking for a photo-generated hole from the quantum dot to be migrated to one of the functional ligands. And as the charge carrier is now sitting on surface out on the ligand, another chemical species can come in and interact with this now generated charge and produce some type of reaction or change the formula of the structure.
I don't know. Is it clear? Did you get what's really happening there?
I mean, I can picture it just because I have an idea of already of photocatalysis.
Okay, but from my point of view, it looks like again, you talking about ligands, you're talking about charge on the surface. So why do you need ligands? So okay, you photoexcite, you have your charge carriers. What's the role of ligands then? Like, why you need the organic molecules there?
So the role of the organic
like,
ligands...
For example, if you look on a platinum catalysis, right? People just have platinum, and it works as a catalyst, right? Even without any photoexcitation. Here you have quantum dots, and you have organic dye or something. So probably you need to explain why you need these two systems, and what exactly doing catalysis in this system. So it's not really the quantum dot with, well, maybe, I don't know, but looks like there might be several options. So you need to figure out what exactly is the system which is used for catalysis in this case. Like, for example, if you're considering water, like again, you can go for many reactions, right? Probably it's a good idea to focus on one. Let's say if we go with water oxidation, just focus on one, right? So for water oxidation, what do you need to make it happen? To oxidize the water to oxygen. If you break it into two reactions, what do you need for this reaction?
Well, you're going to need the charges and the energy needed to break the bonds with water.
How many?
And then stabilize.
Yeah. To break the bond, you need really to have, like, it's oxidation. So you need to, if it's oxidation, do you need electrons? Or you release electrons?
We need holes.
Yeah. Well, oxidation is the loss of electrons. And so depending if you're generating the oxygen, Well, so it'd be 2 water molecules to produce 2 H2 molecules and 1 O2 molecule. So let's see, 4 electrons.
Has to be released, right?
Mm-hmm.
So to make this reaction happen, you need really kind of a source, or not a source, how you say, something where these electrons will go from water molecules, right? Will provide this electron.
You need to inject holes into water
or
molecules.
You can say inject holes, yeah. So take electrons from water molecules or inject holes, right? And actually, this is a role, and again, it can be done through the surface, right? But in this setup, which you will be talking later, it's not really the surface of the quantum dot which is providing this positive charge to release electrons from water molecules. It's actually the dye, which have in a metal positively charged ion, right? Which will be changing the oxidation state first. Let's say if you go with ruthenium complex and your charge is shifting from 2+ to, let's say, 3+, or maybe even 4+, which will kind of will take at least 2 electrons if it's 4+, or at least 1 electron if it's 3+, right? Returning back to its neutral, the most stable form, 2+ ruthenium complex, right?
Yep.
So, because you can also think, the confusion is because, again, you can think that you just have a quantum dot working as a oxidizer or photooxidizer, right? Why do you need this organic dye on a surface? And technically, probably can find literature where they use just quantum dots. Maybe, I don't know. I saw several.
Yeah. So,
but you, if you want to go, you need to be a little bit more focused, right? And then really make setup very clear how your system looks like.
Okay. Well, I'll clarify what I mean by surface. When I said surface, I'm realizing the surface is now the ligand itself. So you're transferring the whole from the quantum to the, and then there's a reaction on the surface of the ligand end, not. So that's the way I was thinking about it. I'll make that more clear.
Okay.
So one of the big benefits of also having a ligand on a dot is quantum dots can be known to have a high energy band gap, and so to enhance or increase absorption in a visible light range, you're going to add these type of ligands to the surface or introduce new electronic states that provide new paths for optical absorption within the total quantum dot complex. This is kind of the introduction as to.
But then my question is, if we have metal organic complexes, which can already work as a photooxidizers, right? You just photooxide them and attach them to the surface, which can be titanium dioxide surface, to the bulk surface, right? So you photooxide, and this is Grätzel cells or something like that. You photooxide the dye. The electron, after photooxidation of the dye, goes to the substrate, providing again positive charge on a molecule, which will work as a catalysis.
Right, because you need
and in this case, you say,
in order to redox.
Well, competition with what? What does compete?
So it's where you can have reignition events, or you can have energy transfer. I mean, where you have both charge carriers migrate to the same material. And so these transfers and these charge separation lifetimes are kind of what give you.
This is already well studied for Grätzel types of systems, right? Let's say titanium dioxide surface, where it has the homoluma and how it's aligned to this or that molecules are well known already, right? So again, the question is, why do you switch into the quantum dots? Especially if you increase it, like titanium dioxide have already the big band gap. If you go to nanomaterials of titanium dioxide, it would be even larger. So what's the reason to switch to the quantum dots in this case? What do you think? Why really we need them quantum dots instead of bulk surface? Looks like it's less beneficial.
Yeah. Well, I mean, I think once you switch to quantum dots, you're now now within the material you have this many more charge generation centers. So you have a breaking apart of a bulk material. So you can have, a single electron trapped within a quantum dot with a hole migrating to the ligands. So instead of having an entire surface where you can have these charges going back and forth from ligand to bulk, it's a reduction of excited state charge carriers that can lead to recombination.
So, John,
You don't like that,
question.
Yeah.
Would it be prudent to say that you introduce states that are aligned properly so you have the electron and hole drive to different portions of the molecule, which then can undergo reactions?
Yeah. So I mean that's the whole point of putting a ligand on the quantum dot, is so you can adjust those states so that you have the charge separation, or the charge transfers.
Okay, so it's more important to have the alignment of the ligands correct instead of decreasing the optical properties due to photoexciting the ligand by itself or the quantum dot.
Yeah, I would say so.
Well,
Okay.
I would agree with you.
technically, it's the main point is that we don't want to excite the dye, and this is why we don't go in the same way as Grätzel type materials, right? Because for the excitation of organic ligands, usually they have the low time for how it goes, well, anyway, so they experience for the degradation.
Oh.
No. It means you can excite it once, twice, and then the molecule will be degraded, right? Because it's just the molecule might dissociate under the when you use it in many cycles of photoexcitation. So, and this is well known for any organic molecules. So the whole point is instead of exciting the dye, the organic molecule, you excite the quantum dot, the inorganic compound, right? Mm-hmm. And again, this is a big difference why this system rather than bulk with a dye, because bulk with a dye, you excite the dye and then you have electron transfer. Here you excite the quantum dot and you're getting a lot of benefits of it. You said, well, quantum dot has a larger band gap, but you can change it with the size, right? Just increase the size of the quantum dot and you can make the band gap smaller. And of course, start with a material which already has a small band gap, like bulk materials which doesn't have a large band gap. Don't start with titanium dioxide. Use something, lead selenide, for example, which has very small band gap, 0.2 electron volts, right? So it's in the infrared range. And then decreasing the size, you can tune the band gap to the energy range where you want to. So it's much easier to, well, I would say, there is of course tunability in the gaps for the organic dyes as well. You just modify the side ligands, the conjugation and so on, right? But quantum dots also will, the size of the nanomaterials will also provide you this tunability, which is very easy to do in the labs, right? So, but you will increase stability of such system when you excite the inorganic material, so therefore the stability will be increased. Also, they have much higher efficiency of absorption light comparing to the dye materials. So it means the surface, how we call them, the surface, optical surface area. Cross-section.
Like cross-section. Yeah.
Optical cross-section is higher for quantum dots rather than dyes. So like you have, again, in your introduction, you have kind of explained why you're choosing this system, first of all, right? And again, there are many setups which you can do to create these photocatalytic materials, right? And they are known. And you can, of course, like you probably didn't, I don't know, maybe you will mention it later, but kind of, as I said, like you can go with a bulk material, you can use quantum dots by themselves, being photex, using instead of dye, you can use quantum dot on the surface of titanium dioxide, for example, right? And then you photoexcite quantum dot, and again, we'll have energy transfer and try to see maybe surface of quantum dot can work as a catalytic agent, right? So there are, but again, you from this broad way, very broad type of materials, you want to focus your research on something very specific, this specific system, and you need to justify from literature what are the benefits of this system, right?
Okay.
Looks like this was kind of lost in your presentation. And benefits deals with the processes which are involved in a catalytic, right? So this is first photoexcitation, and of course it means where you excite and how much stable your system is, photostable. And second, efficiency of charge transfer, and why you need charge transfer. Again, that's again, you need to talk about overall catalytic reaction, right? And oxidation or whatever. In our case, it's oxidation, right? So that's why you need to create these charges, and you need to create positive charge, which again returns us back that if you photoexcite the quantum dot, then it's not electron transfer, it has to be hole transfer, right? So you need to focus not only on the efficiency of charge transfer, so you really want to have a specific direction. You want to have positive charge go to the die, not the negative. And if negative goes, it's bad, right? You really, it means your setup doesn't work, or like energy transfer, competing processes. Okay, so this thing has to be, you need to rethink about it, and probably also add some papers for the discussion on these processes and different types of materials which can be used, and again, justifying your approach for this specific system.
Okay.
And then you can go with your applications overall. Or whatever you order, you can start with your application, but looks like this part is missed. Well, I look on your slides, looks like you never really go to that part.
Okay. So with some of the things that we're interested in, that I'll try to touch on with some of the papers that I'm going to highlight in the literature review. So there's a range of quantum dots that have previously been studied, and so I mentioned cadmium and lead chalcogenide type quantum dots. There's also cadmium oxide and also zinc oxide quantum dots that have also been previously studied. And so, like we mentioned a little bit earlier, depending on quantum dot composition, your quantum dot size, it's going to provide a unique electronic structure. So it's the tunability with specific wavelengths that we might be interested in. And they're also going to have different surface reactivities and the way they're specific ligands being functionalized onto their surfaces. Second important point is the type of surface functionalization. So which types of ligands are we going to be looking at? So each of the dyes are going to contribute electronic states that are going to have a varying alignment with the electronic states of the quantum dot. And so this is going to be one of the most important points in the ability to drive some type of hole transfer from the quantum dot to of the ligands. And as I mentioned earlier, they're more specifically, we're going to be focusing on metal organic complexes. And some of the characteristics that we already discussed, because we were looking for absorption occurring solely in the quantum dot, we need a visible range, ideally, for optical absorption to collect the most light that we can. We want to keep these things stable. But what's also important in these uses and also in the ligands themselves is the overall charge that's found to be on the ligands. And so we'll touch on some of the cases and how charged ligands can actually enhance whole shifting of electronic states and energies. And also how those shifting states due to this added charge is going to relocalize some of the density for the HOMO levels, and looking at some type of hybridization between the quantum dots and the ligand systems, and also solely a ligand going from just say like the null compound having a hybridization with the orbitals also on linkers themselves. I'm also going to touch just a little bit on the solvent effects that have been studied. Still trying to draw up a plan on how we're going to approach solvent effects and what that's going to look like for now. Also, earlier we just talked a little bit about different competing mechanisms. Ideally, we're looking for whole charge transfer from the quantum from the ligand. What mechanisms with this are going to be energy transfers. Depending on the electronic structure, we may run into things such as trap states, different rates of non-radiative relaxation, but also with trap states leads to non-radiative recombination. And so those are all things we have to kind of keep in mind as we're trying to make a plan to what systems we specifically want to start with. So this first slide is just an image of one of the sensitizing molecules. I believe it was K77 from one of Gratzel's first DSSC cells. And so we've already mentioned that we're not looking for the same type of effect used in DSSC for functional absorption of the complex. But to provide an image of kind of some of the background for where these ruthenium complexes come from. And so you can see there's groups added on this ruthenium complex, and I want to highlight those as well as these carboxylic acid groups, as those are going to be important going forward to how the ligands are binding on. So one of the first things I want to mention was some work done by Klimov and his group. So what I wanted to pull this paper and highlight for you guys is look at the different modifications someone can put on complex to modify the electronic structure of the ligand and how it's going to interact with the electronic structure of what we're in. You can see that going from left to right, there's just a bipyridine complex, but then you're also adding in 1 and 2 carboxylic acid groups. And so with the addition of these carboxylic acid groups, whether or not they're protonated, is going to affect the overall charge of them and how the states energetically align with those of the quantum dot. And so that was it was kind of a shorter communication paper, but that was one of the main highlights, showing the shifts in energy levels due to specifics of ligand. And so this type of idea was done in collaboration. So Professor Kalina and co-workers, they looked at both experimentally through calculation and looking at these different derivative bipyridine complexes. And so one of the main things that I wanted to highlight out of this paper, and that's something that's going to be important forward, is how when you're looking at these bipyridine complex, how the carboxylic acids are binding to the metal ions on the quantum dot. And some this kind of top left figure bipyridine derivative, and then the bottom left image is showing 3 different variations of how these carboxylic acid groups can bind to, in case they were looking at cadmium-7. So the state, just the metal center, a bridging system where you have both oxygens from the acid binding to 2 metal centers, and then you have a chelating ligand where both oxygens are binding to 1 metal center. From their work, the main point that I want to highlight, at least for now, is that the binding method was found to be bridging. So you have both oxygens two separate metal ions. And so I don't know if you'd like to add anything, Professor Kalina, but that's kind of what I wanted to highlight out of this paper, at least for now. Okay. And so one of the next papers was also done, is computational work done by Professor Kalina and co-workers. Again, looking at variations on substitution in these bipyritives and how they're binding. So you can see on the top left imaging, you're looking at a bipyridine complex, then carboxylic acid, and then you're adding two carboxylic acids and methyl groups. And so this system, and looking again at the three different methods of binding within the systems. So also looking at some of the zinc oxide materials as well. And I think I put another, oh, thought I added one more image. And so the image, you can see, I thought I went up there. But one of the things that I wanted to highlight here was about our discussion of how the energies of the states between the quantum dot and the ligands are interacting with each other and their relative positioning. And so you can see in this image here, the red states correspond to those of the quantum dot, the blue states correspond to those the ligands itself. And you're exciting, you know, from the quantum dot to the quantum, the ligand energy states are buried far down in the valence band. There's no possibility for any type of whole transfer going the ligand, and that's our main goal in looking at systems. And so absorption occurring on the ligand itself is resulting in you know, some type of high energy excitation, the conduction, but still the electron passing back down into the quantum dot. So with these types of systems set up that we'll see a little bit later in some analyses. And so more papers, so they're still looking at all these different types of ideas. The one on the 1113 is looking at optical characterizations of these whole extractor materials for CAD selenide quantum dots.
John?
So, yeah.
I think we have a technical issue. Your slide is not really changing for a couple of minutes, and I think you were talking about different slide now. Right?
We're still on Wagner.
Yeah, we have 2011 Langmuir.
Okay. Well, I'll stop sharing and I'll restart again and see if that helps.
John, we all have your slides printed.
But they're very little, it's really hard to see. Even images is hard to see.
And I think well, this is a version probably, I think, what you have as well, so.
Doesn't want to share anymore?
I would say it looks like you guys.
And we also have, probably it's not very fast internet or something.
Yeah, it is not a... Which date is today? Is it 13? No?
It's 6.
Okay, should go up.
Yeah, this is annoying.
Well,
then stop sharing and just keep talking.
and then just tell us which slide we need to go, right? So we can navigate through the prints then.
Okay.
Title of the paper. my work, since I think pages are not numbered.
I was say that's why I was gonna say on the file I have everything should be numbered, and there's gonna be some different things. I'm gonna see if I can load the stuff in instead of my PowerPoint. Okay.
But
well,
are you in which journal are you now?
Let's go past Langmuir. So we're still in 2013, looking at the paper for BC.
So which one?
This
Physical
is
chemistry C?
Okay.
Actually, there are two of them, 2013, 2013, physical chemistry C. Maybe give us a title.
That's all studies of grounds of quantum dots function by ruthenium-2 polybipyridine.
Okay.
Okay. So here, this is what I was just talking about a little bit earlier, and you guys couldn't see. So instead of looking only at just the lead or the cadmium selenide, now we're switching and looking at lead selenide zinc oxide materials with these types of derivatives, and how varying monodentate, chelating, and bridging ligands play a role in the densities and electronic structure. And so one of the main things I wanted to was that we're looking solely at carboxylic acid type linker groups onto the lead selenide, and so excitations from the quantum dot to the quantum dot are no longer, well, they're not going to provide any type of hold charge transfer because the ligand states is above the top of the valence band, so there's nowhere for it to go to on the ligand, and a ligand to ligand type excitation promotes a relaxation of the electron from the ligand back down into the bulk of to the quantum dot itself, and so just like the very material choice for the quantum dots is highly important in directing the type of charge transfer that you want to have in X. The next paper I have in here, 13. Well, which do you guys have on your page?
We have all. What do you mean?
Was there a second J? Right, you said that there were two on your page.
Well, we have 2013 physical chemistry C for ultrafast Hall electron transfer dynamics and Katz-Leonard quantum dots synthesized by Piragello Red, a supersization system.
So,
John, I think there's also a photo-induced formation of bithiophene radicals.
Oh, it's on the same slide, yes.
Oh, he's frozen, I think.
Yeah, we have problems with connection. Probably.
So our internet is fine, right?
Our internet is fine because we have no problems with Levi. Yeah, we see you.
Oh, there he is.
But he's still frozen. John,
no.
Are you here? No.
He was colored, now he's black. Oh, now he's back. John, so there is the photo induced formation of bithiophene radical cation via Hall transfer process in cadmium sulfide nanos. Oh, he's freezing again.
Okay. Okay. Yep. I know where you're at. I'm just pulling up the old. Okay. I'm going to do formation of. This was something that, again, they're using. Well, now they're looking at cadmium sulfide nanocrystals and these bithiophene materials. Is basically the smallest type of thiophene that they can use. And it's also known to be an electron donor. So,
So what should we do? Should we switch to Levi and then leave him for Friday?
Well, it's already
I have.
an hour.
I already have. I have a meeting in 5 minutes.
Okay. Well, it's your call. So what we're going to do now? Because
John,
I think it's really very painful to listen to.
John, can you summarize your conclusions?
Summarize your conclusion.
Okay. Well,
please,
okay. Yeah,
please
that's fine. I'll just do that.
Slowly.
We just cannot really listen to you because you interrupted, right? So like we hear only second word. Each second word
Cutting out.
is cutting out, yeah. And you freezing again.
Talk about my.
What? Okay. John, can
So
you hear
there are
us?
things as. Yes.
Yes? What about now?
Yes.
Okay. Since it's time.
I think we should thank John for a very important
Well,
effort.
let's try on Friday, starting with these slides, whatever it is, one of these 2013 slides for.
By beat thiophene.
Okay.
It is the last word that I was able to understand.
And hopefully,
Okay.
what's going on with your internet? It looks like it's a problem with your internet. Is it so slow?
I don't know. Like, it's been fine the last few weeks because I went and got it put them, and I haven't had any issue with it until today.
Is it
I
possible
don't,
to fix
I don't know
it?
what this.
Is it-
I mean, I can reset my router, and
Okay.
I can be.
Try to do something with it by Friday. Because otherwise it's really very painful to listen when we can hear only each second word. Maybe each said.
Okay.
Okay, but thank John. So we will continue the presentations on Friday. So definitely there is a Levi. There are leftovers of John. And maybe there will be another volunteer. Maybe not.
Make a first approximation of a good introduction.
Okay, and now let's just practice helping each other on the literature review. So you do have the forms. So you read through the figures and try to, if time is up, and time will fly very quick, just mark on this list what you like or what you dislike in the figures of the manuscript they're looking. If you have more time, you can write with red or whatever color on the manuscript itself and generate feedback that, on your opinion, will improve it. And then tear it on pieces. Right now it's bundled together, but we need to staple only one piece at once and then return to the author. So that author reads your feedback and improves whatever is going on.
Can you hear me better now?
Yes.
And we can see you better as well.
Can you hear me better?
Are you connected to wired internet instead of wireless?
Yes, I plugged in.
Need to do this way.
I'm back to the couch. Yeah.
Okay, long live the couch.
Long.
So, okay, let's try Friday with a couch.
Okay. Well, otherwise, I was going to say, do you want me? Can I give my kind of main conclusions, and then maybe I'll just come up Friday and we can just discuss the rest of it in person.
Yeah, you can express your conclusions.
Okay. So I guess kind of the two main big points from all the literature that I skipped was that there's a lot of effort that's already been done in understanding like the oxidation precursors and looking at how different organic compounds react under redox conditions. And there's also been a lot of effort already put into understanding electronic structures of ruthenium derivatives and how they interact with the electronic states of different quantum dot materials. And so how is it that we can combine those two main types of understanding to build the best type of photocatalytic complex possible? And so what we're looking to do is basically take some of the understandings from what provides the best type of orbital overlap between a quantum dot and a ligand, what type of linker agents between the ligand metal center and the quantum dot to provide this type of whole charge transfer, and then go ahead and run dynamic simulations to calculate the rates of these whole transfers and compare them to experiment, because that's one of the things that's missing. There are specific mechanisms that they can measure experimentally, but sometimes due to the lifetime of these types of transitions, there's limits on how fast the spectroscopy is, and so we can provide insights onto really ultra fast systems, but also to I'm trying to understand some of the chemical mechanisms that lead to these types of ultra fast systems, and also exploring systems that haven't been studied experimentally yet. And so looking between ruthenium and iridium complexes, organometallic complexes, to try and increase this type of whole charge transfer between quantum dot and a die. Okay. And then, so kind of how to address what I just mentioned. Taking all this information that I was trying to present today, and building these new models that probably have negatively charged overall ligands, ideally have sulfonate groups attaching to the surface, because that's what's kind of been trending even in some of the newer literature. And then taking all this knowledge of, like I said, these binding groups and these ligands, and just trying to wrap it all up and use our methods, which haven't been done yet. I know there's been some non-adiabatic work done in Oleg's group, but it hasn't really been for this type of process. It's been mainly looking at just some of the quantum dot materials themselves. And so providing this type of non-adiabatic relaxation dynamics and charge carrier lifetimes for specific charge transfer events is what we'll be able to give to the community. So those are kind of my main conclusions. And like I said, we can go over more details, I guess, when I come up on Friday or from the couch on Friday.
Just a note to you, maybe it would be better if you can focus, again, thinking about that you cannot simulate everything, right? So you need to start with some structures which you're probably looking on the literature, to just give a few, maybe 2-3 structures.
Okay.
I don't know, 4 is maximum probably, which you think is the best choice to start with, right? Like this, especially in the terms of ligand, what kind of ligand modification you want to check, right?
Yep.
And maybe wherever your candidate for quantum dots. Would it be cat sulfide? Probably looks like you have a lot of papers on cat sulfide or something. And again, this would be finalizing the discussion on the literature now. We know this information from literature. You can focus now, say, no, this is open questions, and we will address this question specifically looking on this ligand, right? Over on this dye, with this metal, with these ligands, or maybe modifying these ligands, putting these groups on this basic ligand, right? And on the surface on this type of quantum dot. So
Okay.
for Friday, if you can really focus in on a specific ligands and specific, a few samples of specific systems, I think would be really great.
Okay.
Should be
No, that-
No, I have a question.
Oh.
John?
yes.
So it's for my curiosity. It may be a very silly question, but if you're looking on photoelectrochemical reactions, they typically are closed cycle with oxidation and reduction side.
Right. Looking at cyclic voltammetry graphs.
From what you were showing, it looks like you are putting only one type of ligand, to my understanding, mostly for oxidation part of reaction. How about the second part? Does it mean that you want to place ligands of two types, or quantum dot is adsorbed to something else? How do you see it?
So the number of ligands on a surface and multiple ligands on the surface are all going to play a role in the overall ability for transferring specific charges. And so I know in reading some of those, in going upwards of, well, one, it depends on the quantum dot size. How small is it really going to be, and how many surface ligands can you load it with? But it's also that, the rest of the surface has to be passivated with something, because otherwise you're going to have some type of probable structural modification that isn't correct. If you're asking about, putting two different ligands on, both with one being an electron acceptor and one being a hole acceptor, I don't know, maybe it could be interesting. But if I missed the kind of point of your question, then I apologize.
I think his question was what you're going to do with the second part of the reaction, right?
What am I going to do with the electron?
Reduction.
Okay.
Reaction. And the answer to this question, you kind of already said. Technically, yeah, we might, and there is some papers. Actually, I was reviewing recently a paper. I think Jabet was helping me, or maybe not, don't remember. Maybe I just did by myself. So they use cat sulfide quantum dots for the photoxidation of, how it calls, something dealing with...
Methyl and blue?
No. It deals with oxidation reaction for... something done from the wood.
Okay, lignin.
Lignin.
Kind of to cut it into the smaller size carbon-based whatever molecules, right? For further use in gas or whatever, gasoline, and so on. So in this case, they were claiming that they were able to have. It's not it's photoxidation, but not for the oxidation of water. It's completely different molecule and completely different reaction and mechanism of reaction. And they were showing that this reaction happens extremely quick, means hours, and it was quick.
Oh, okay.
But the reason why is it, and much more efficiently comparing to the standard ways of standard catalysis, because they take completely different mechanism, and in this mechanism both electrons and holes were used. Like one intermediate was created through the electron transfer, and then another intermediate was created from hole transfer, and kind of because both carriers were used from the photoexcited quantum dots, the overall, so you're losing really nothing, and the overall efficiency was really very high, and mechanism was completely different and much quicker comparing to the other things. So technically, you can think about some applications when you can employ both electron and hole transfer, means both kind of reduction and oxidation reactions to occur on the same quantum dot surface, right? Maybe again playing with different ligands, or depends on a type of the reaction you want to. Another approach would be just split it, right? Same as in many cases, you really can hold separately the part which is working on oxidation and the part which is working on a reduction, right? Kind of you make them separately and then you recombine it kind of together in a circle. So again, this technology is also known, and you can find how people address these questions. Or, for example, there were work when they use nanorods of cat sulfide nanorods, and then they have a catalysis on one side for the reduction, and attaching to the other side something dealing with oxidation, and you kind of separate it through the size of your nanorods. So in other words, there are different approaches, and again, you can overview it, means you need to know about it then, right? If you work in this area. But you, of course, for this specific research, you have to focus on something specific. You cannot do calculations for everything.
Yeah.
Did we answer your question?
Yes, you did.
Yeah. Okay. Well, and like even a couple of the newer papers, so with their catalysis, they're putting nickel adsorbing to the surface of the quantum dot, kind of in small quantities, and so they're getting an electron drive. I mean, it gives an overpotential to put the electron on the nickel and allows the hole to transfer out and react with. I think they had like ascorbic acid or something in their reactions.
So you're saying they dope with a nickel, or it's just attached atom on the surface?
It's attached. It's attached on it. Yep.
Interesting.
Let me see.
Well, if you have this paper, we probably can discuss it on Friday.
So, well, it was actually both of these papers. I don't know if you can see my PowerPoint screen.
Now we do.
Okay. Yeah. So there were two papers that were actually doing it. So one of them was one you had sent me this down on the bottom, the oxidation of the alcohols. But then this other paper looking at, this nickel generating these hole trap states. And so the schematic is kind of this top left. And so that, the hole transfer to like this hole trap state and the electron transfer to this nickel state are two processes that have been promoted, and everything else has basically been reduced within the material. And so, that came up in a couple different papers. And so I don't know if that's something we'll want to look at in, just putting a nickel atom or something.
But this is definitely interesting, especially taking into account that this is kind of really very recent paper, right? So this is probably also we can easily model with our models and something new to add to the things which we have already done before, right? So I would say, this is for sure very interesting. And again, you have to, from this big broad approach to seeing everything, what maybe not everything, but at least as much as possible from this review, which you have already done, right? So then really try to focus and say, well, you choose just from your point of view, because you really, I didn't read some of these papers, especially the recent ones, right? But you did. So based on this, make your own conclusions that you think would be really kind of our first priority to check, right? Let's say these structures, for this ligands, for this surface, maybe attaching nickel looks like might be also interesting idea to do. Yeah. Okay, so let's finish it on Friday.
Okay.
Okay, let's thank John once again.
Oh no, we uploaded already.
We uploaded. Brandon Gifford was watching recordings of our last meeting, and he liked how we uploaded 2 times.
He left the comment, right?
Comment, yes. John?
Yes.
And you can download the materials that we are overviewing now online through the links.
Okay. Well, then I'm going to go back to my desk. So we'll see once if the connection lasts. But if not, I'll send my scanned comments back to the authors.
Yeah,
so.
I think it's okay if you kind of get out from the connection. Okay. Okay, thank you for the presentation. See you Friday.
Yep. See you.
quickly go through the figures which I have. So you can see my comments. Okay, so here I suggest just to show optimized structures. This is unoptimized, because it's clearly showing what is ABC. But then it would be interesting to see how this guy is changing when we optimize it. Right? We'll have to write a short paragraph when we do, the pitch figure. You will have to describe, and not just describe, but also describe means just, oh, we were doing this and this as shown in figure 1. It shows, and then you just describe, right, what is showing there. But you also need to analyze, and for analysis means like you say, oh, as you see, the optimization results on a significant change, because especially these structures are not as beautiful anymore, right? There. And this one probably not so bad, right?
Yeah, it just
diagram again.
Well, again, you need to choose representative one, right? So that's why whatever your choice of solvent, if you want, you can, up to you, right? And then of course if you say optimize structures, then you probably need to say in this solvent, right? And I would say probably use the same solvent for both of them. And I would,
Right.
I don't know, I'm still kind of
It's kind of writing
not
like,
sure,
like you said.
but you
like
have
chapter
absorption
by
spectra
chapter.
for single ligands, right?
Yeah.
Yeah, I have some.
What you were showing in a poster.
That's up for we fully passive.
Oh, you didn't show any single one, but I think I saw it. Or maybe it was those. And again, this is for fully passivated, right?
Yeah.
Yes.
So we
Yes, the
still
direction
didn't
of the
decide
paper
whether
is
we go this
very-
full, I'm still thinking we probably go just with
A cheap model can approximate.
Also,
Ratio.
I went to
That's
another
like one narrative.
conversations and
So we can try to
wrote
follow
this
what you're
down
doing.
for just today.
it's under the maintenance.
I'll
Yeah,
keep
so
that in
we're
mind
gonna
whenever
be
I'm talking to them.
that in tomorrow, something like that. So.
But again, we're still kind of in the process of deciding whether we go I didn't send you the paper from I just forgot. I will try to find it to remember it. I will send you the Nadine's paper, right? And again, so two things what we can do. We can add, again, maybe not all of your results, but we can add some of your fully persuaded results on cancel file. Like versus trial. Together with these figures on cancel. Cancel, and then we're comparing effect of different solvents, right? And again, talking about this network formation. And then the effect on the absorption spectra in cancel optical properties, right? Catselenite versus lead selenite.
Okay.
And it looks like they're not maybe very different, but there might be some difference as well, right?
Yeah.
So we can go either this way, and then this data will be connected to this paper. Or we can go with putting everything together, single, longer one, because then we will have absorption spectra and those to add to this one when have. And again, you were showing it to me already, I remember, probably, and I think it's also in the poster, right? The most representative one for your dose when you have a single atom,
Yes.
a single ligand, right?
Yeah.
So it looks like this is very easy to add, and you have to add it anyway.
Yeah. I was going to.
Yeah,
I just
so I would say after figure 4, right? You probably
Yes,
need to
that
have
was-
figure 5 would be your dose with maybe a few structures, right? With a few representative
Yeah.
structures, and you have to.
Yeah.
So we don't need really structures with one ligand, right?
Yeah.
And kind of the same for the fig 6 would be for spectra, fig 6 for this absorption spectrum. And again, I would suggest probably choose exactly the same structures as you show in the dose. Easy comparison, right? And then the other ones, you can add to the supplemental materials, all your doses and all your absorption spectra. Or you can show not all, you can show only those which are not shown on figure 5 and figure 6. Up to you.
Yeah.
And then this would be the end of the story, if we have enough things to say.
Okay, and then if I wanted to,
Or we really make it longer and say, well, here is one ligand, now we're adding the second ligand, right, and see what's going on, many of them,
Yeah.
completely fully passivated. And again, talking about network, like you already mentioned it here, one of the structures definitely showing.
I didn't add it on my poster. I had like a computer. Do you want me to add it on?
No, I will,
Or not?
we will go through it very quickly.
Okay.
But as I said, like right now, make it as one, as everything as one story, right? But when we will have all figures, and again, looking at them, for me, would be very easy to, for you hopefully too, would be very easy to see that, oh, looks like we have enough, like this is really very nice story by itself, like there's definitely
I have a quick question
1,
about
2
calculations
points,
for class
good enough, like,
So,
I'm not sure
Charles
right
said
now
maybe
it's
this
really
time
good
we
enough, just
geometry
after you
optimization
have
or
fig
models.
5 and 6,
We can
but
just
here
use
would it be
the-
really
just
enough
use the
Yeah, I haven't
Physical-
analyzed any of the
physical
GDST
meaning.
for
Like it
the
sounds
single
reasonable.
point.
Oh, okay, but that's why I said like hopefully,
Yeah.
because I think your dose was pretty much showing all the trends, right?
Yeah.
And hopefully we will see pretty much the same trends in your absorption spectrum.
Yeah, yeah, I can do that. It's gonna take me a while because the GDFT
Oh.
is hard for me.
And again,
So-
don't worry, Dimitri is trying to push with his deadlines, whatever he said,
Yes.
whatever it was. Yeah, but again,
Yes, that's
It's
my
a solved
that's my
deadline.
point.
Okay.
So
we're
I
not
did
going to
calculations,
submit it
I
to
have
the
the
job
unit
right
cell,
away.
Oh,
and
okay.
So that's why,
and some
but it's
battery,
good to have a
and I'm
deadlines
doing geometry
because
optimization.
Yeah.
otherwise
That's
it
a
will be
huge
never
difference.
happening, right? So
No,
we
that
need
makes
to
sense.
push ourselves.
Like disorder.
So that's why I
it's
said
reasonable.
it's a soft deadline, right? So don't worry.
Okay.
But these things you
And
probably
I-
can work on Thursday.
Yeah.
If-
Um,
I can definitely
because you
learn
have,
to
if you
analyze.
have all
Put
that,
one
it's really just
carbon
making the nice
dioxide
figures.
Mhm.
on the
And looks like
surface,
again,
one
I remember
heating,
we discussed
and
it
I
with
do
your
see the
dose and it was
absorption
pretty clear
and the
kind
absorption.
of idea. If this, then
So-
that,
Does that
if that.
transfer?
I did
Yeah.
through the
Except
both
for
layer,
when
one
I got
layer
to
is
the
metal.
class, I
Well,
knew it was
yeah,
different.
and again, those were kind of,
molecule
in
and
agreement
all
what we were expecting
So
from
for the
them.
metal one,
So I would definitely say focus on
absorption
Thursday on this
when
one
you
and
have it
probably
at
also change,
six-
go through the
500K.
changes which I have here.
Okay.
And this one, just leave it,
Seven,
and this
okay.
would be, like, it's good, you
Okay.
even mark it with
But
a
for
different
the
number.
organic
Oh, yeah, I had no
material,
idea
it's
what-
difficult.
And then
Right.
absorption spectra for this one, I would say
Like,
we,
maybe
we might probably
1100 maybe?
retake it
Mhm.
and put it in the other paper,
Yes.
or
So
maybe
just
stay it
my
here,
question
and
is,
then it would be just get on that. In
what
other words,
kind of
for you
information we
it
can
would be
get
either
from
two
our
pages with your
calculations
whole thing,
to help
or
our
just one.
experiment?
So, but
And then, yeah, I don't know what I did wrong. So,
well, just that's why I said just recalculate, right?
yeah, that's
It
what
might
I'm
be.
doing.
I don't know. I have a
I
feeling
might have to
maybe you
leave, I look
switched.
over.
Maybe you switched to the different bases.
I
I
haven't
mean, not
used-
bases. To the different functional, no?
No, I
Because it's
haven't.
too much blue shifted. And I can explain why. Like you said, like my email didn't make a lot of sense. But look, so and you didn't read your old absorption spectrum, but in your old absorption spectrum, like acid, whatever it is. In one, yeah, propylamine is fine. I mean, looks like we don't have issue. At least I don't have issue with that. And for acetonitrile, right? So your spectra was
The file was,
yeah. So
Mm,
I don't remember exactly what the
That's what I
structure,
have
but
is-
like
how
something like
reliable
that,
is
right?
our
Yeah.
data in
with
terms of
really low
temperature?
transitions here.
Um,
And the red ones were also having all low transitions, but they start somewhere, let's say 3 electron volts versus 2.5 electron volts. I don't remember exactly the values, but
Yes,
this
and
was
yes,
sialate, right? And this was sial. Now, if we look, and this was in this solvent, right? If we look on your dose, so this is your acetonitrile, this is acetonitrile.
yes.
And I would, I really like how you did it here, right? Like you put it in a, I would suggest also put your A here and A here, so it will be clear, right?
Yeah.
I like how you did it here, I would suggest to do it, well, here you can, but here again, reorganize it, and you can also make it as 2 columns, right? Propylamine,
Okay.
acetonitrile, because if you put it in this way, kind of awkward. So maybe reorganize it so you will have A and B as a column, and then C and D as a column, and then this would be and you will hold the same kind of, or your A and B probably has to be here. Yes, right. And don't forget to add A and B, because here you refer to some,
results at 250, so it's
yeah, you have A and B, but you don't have A and B.
it gives
Oh.
So then it's very confusing
Yeah,
for people.
yeah,
So
that
what is A and B? But anyway, yeah, so this one you can probably reorganize, but go back to the issue which we have. So if you look, we are comparing this versus that, it's the same solvent, right?
So how the disruption
Yeah, also I need to change the gray, because the gray,
experimental
you see it.
Right, and I have it here. And maybe change green to the blue again for the colorblind or something.
Who faces technical stay on shoulders of giants.
Yeah, it does make sense. For your SIL, because technically what happens in am I true that
And
in a
also, I
synonym,
know
you said
the
in a
calculation
synonym
is
trial, if
just
you start
one
with
single market.
SILE, it stays SILE.
No, it goes to filate, it's the conversion from filate
Then it stays
back
as
to
SILE.
file.
So because it looks like, because you have a conversion here, right? So it looks like we have really a lot of them converted, like this is really, you have majority of them being SILE and a little bit in between, right?
Yeah,
Not completely disattaching, but this is what we call the network, right?
yeah.
Here it looks like you have really majority of them converting to the silate, right? And here they stay as silate, that's why you have such a big peak here.
Yes.
And here it's much smaller, right? So we understand the dose. And then this also explains why your band gap, like if you look from here to here, and of course you can look on the actual values to have your band gap. By the way, you probably can show this band gap. So HG equals, and then whatever your number.
Okay.
Why not?
Why not, right?
Because then it's clearly telling me that this would be smaller than that one.
Yeah.
And the same here. And this will be very comparable.
So do I just take the first one up then? Or do I just take the first one?
No, you need to take these values from actual
Okay.
band gap, right? So it means you need to go to your homolumen orbital energy, right? And then put it exactly, because this is because we widen it, like it's kind of, and you can make it large or small, right? You can dress it with light widths or small widths, it's really aberrant. Yeah. So that's why this age is kind of very different. But homolumen energy, this is what exactly probably, and again, this is why it's not so easy to figure it out what would be exactly the number, because of this dressing thing, right?
Yeah, that makes sense.
The widening due to the Gaussian curve. So, and I still didn't send the work to your professor.
It's okay. You'll get around to it.
I really feel like, should you
I mean, it's really not a big deal. They drop
Also
two
for
at
the
the end of the
calculation,
semester.
right now I just use the gamma ball.
Sense on all of other ones.
So for this kind of
So
calculation,
it's-
do I use to with k points?
but you can do it much better anyway, right?
I
You
can
train-
yes, I can do
Okay.
it much better now. It was
Yes,
the old review of the product world that hadn't gone over it, so.
Okay, anyway. Yeah, so put this in, put kind of arrow for defining what exactly you mean by band gaps, right?
Okay.
So, what I'm saying. So now you will see that, yeah, here the band gap is higher than this one. And I think in your absorption spectra, that's why you have your black curve, you know, probably, I mean, being shifted to the blue, and this one shifted to the red. And if you remember, your red were really very small in intensity, and your black were high in intensity. And again, because it's more delocalized character, we don't have really, like these green ones, they're really localized, and this is what you show in your structure here, right?
Yeah.
So for your silate, they're really sitting just on a molecules, right? Here they have some contribution to your quantum. Here. And acetylnitrile is the same, very trap state, and here it's really on a quantum dot rather, and this is very delocalized. Well, your electrons looks like they're delocalized, but your whole.
But we do have
And
that.
for this paper, and again, for paper, like for post, I said I like that they're different. But for paper,
Okay.
there might be an issue for me because they might ask why they have a different, so probably make the same, same color scheme
Okay.
for
Pretty sure.
both, or whatever, for A.
So I guess I'll just organize the data so I can show it to you.
Yeah. Because there might be an issue right away, they say, oh, why is it green, why is it blue? I would say, just traditionally, probably better to show the same one. And you can play with, I don't know, you know how to do orbital transparent?
Yeah, it's just a slide.
I kind of like transparent, I know some students don't, like, Levi was saying that he doesn't think it really helps.
Okay.
So I don't know, but you can play and you decide by yourself. And also, I would say, in your case, because your goal is to maximize, kind of really to take all the white space, right, and really maximize your figure. So it looks like if you increase, looks like you have this a lot of white. So if you increase it, really taking the whole thing, you still, your image probably will take this much, right? So it looks like it probably still too small. It's really hard to see what's going on with these atoms.
Okay.
Because here you really want to see where they are located.
So do you want me to?
That's why I'm kind of thinking maybe in this case, I mean, I like this propyl acetylnitrile columns, but maybe in this case, if you align them not this way, but that way, maybe you can, like, this helps you to increase, then you will really can take the whole page, and you will have better increase rather than putting it there. Or maybe I'm wrong, maybe you still.
I'll do it both ways, see how it looks.
But again, you understand your goal, right?
Yeah.
And I would say, if you go with this one, since it's exactly the same caption, you can skip this, right?
Yes.
And you can decrease the spacing, put them closer, and maybe you can really just put it. You can really put them one by one side, right, and just make this double, of course, double line, right? And then here it would be bolded, yeah. And this would be an in, and this is again your A, and this is your, if you do it this way. So this helps you to take all this extra white space, and then you make them wider, and this probably will be enough to, and again, if you really, like, for your figures, nothing wrong, because we all, like, actually, all of them well seen. This one is not so much important, although I would probably also suggest to take larger. I mean, you just need to increase it.
Yeah.
Because your reviewers, they will read your paper not in the form of the final nice aligned paper in a columns, as they usually publish in the papers, right? They will really see this draft.
Okay.
This is what we are submitting.
Oh.
I mean, I know some people, like you, of course, if you want to, you can put them already in a column, in exact style as required for the journal. But ACS journals are not so much picky, and this probably will go to Journal of Physical Chemistry C, at least, as a low score. We might try, I don't know, we might try higher than this. And they usually don't require anything, so means you really can have one page, one figure, and caption, right? So don't split figure from caption.
Okay.
But you can really, like, you don't need to have.
I was just trying to keep them small. I don't
Don't.
really know what my
I mean,
requirements
and again,
are.
it looks like this size really works, right? This size works. Even this one is working.
Yeah.
Means they
I
can
tried to
really.
make them clear.
But again, to make your reviewer life easier, so they will not go this way. There's no any limit, so you can. I would suggest have figure 1, page 1, figure 2, page 2, and even if you have such a small figure,
Just blow it up, why not?
make it huge.
Okay. That
And
sounds
then a
good.
caption, not a big deal. So just go with lesson drawn, as I said, because this is showing that you kind of probably in a real actual size they will be having this size, right?
Yeah.
And they clearly see.
Yes.
But for reviewer purpose, so they will not spend so kind of like this. Fig 1, then fig 2. This will be your fig. Okay, so you the next page. Okay, returning back to my question. So as I said, so these orbitals, they are delocalized, right? As we already said, definitely much more on a quantum dot. So that's why this transition, and delocalized means this is quantum dot state, right? It's on a quantum, and all of them is on a quantum dot.
Yes.
So your electron is on a quantum dot, and your hole is kind of here it's on the ligand, right? When we calculate the optical transition, the transition dipole moment, it's really, well, you take a previous class, so maybe you will be not so much surprised with these notations. No?
It is what was in today's class, which Alyssa.
I was not there.
But you can recordings, it was exactly on this notation for this purpose.
So roughly, I mean, technically it has to be corrected through, well, so this gives you this intensities, this peaks in your false peaks, which you show in the actual bands, right? They're coming from this type of information. And what does it tell you? You take the orbital, right, which depends on R,
Or if you want
and you
me
take
to
another
scan
orbital
us.
which depends on H. Technically.
You can
And
do, okay.
like,
Then you will.
in other words, this is the same as you just take integral.
Okay. And establish better good relations for working together.
Like this, because each of them depends on R. It can also multiply by R. Wherever your function depending on R is in this case X, Y, Z.
So if you scan and send,
Yeah.
So it's a space vector, right?
they will appreciate it and
R equals
establish better connections
square
for
plus Y
for
square
them all
plus Z.
together.
And if you know how it looks like, in other words, you know the function depending on R, you can visualize that it has a form of some function. Technically, you can take the integral, you also can say it's kind of overlap, multiplied by R. So if this wave function is localized on this part, and this wave function localized on a completely different part, so like overlap, when you take this integral, it's really kind of overlapping these orbitals, right? They definitely will have any overlaps well, you have a little bit on this, or maybe it's sulfur quantum dot. Again, that's why I said that you need to increase it because it's hard to see.
Yeah.
Looks like you probably have a little bit on this surface, right, and this one having a little bit on that surface. But definitely, this is negligibly small. So when you overlap these orbitals, the overlap is almost zero, right, because they are sitting completely on different parts. If you overlap these orbitals, because they're already taking the quantum dot and the ligands, and this is only quantum dot, but the whole top thing of the quantum dot will be overlapping, means you will have a value in the integral. Right? So that's why this guy will be having larger value, and your peak will be higher than that one or that one or that one, right? Where especially that one, because they're completely localized. Things that have nothing on the surface. Right?
Yeah.
This is a little bit, and again, this is a little bit, but this is almost nothing. So that's why I would say, just looking on your doors, we expect, because this is delocalized, so your loss transition will have some portion on a quantum dot, as we already see here. And this transition should be optically active, means this transition dipole moment, the overlap between orbitals, is not zero. Here, it's clearly on a quantum dot completely, on a ligands completely, right? No contribution in the red, negligible contribution in the red. And again, we see it's a little bit, but really negligible, right? But this one is on a, so this transition from green to red will have your dipole transition dipole moment being almost zero.
Yeah, and that's what we saw in the 2D.
Yeah. And then those which are bright probably will come at high energy, red to red. And that's why for your propylamine, you have your black curve for sials, blue shifted, compare and high intensity, rather than sialate, they are red shifted, less energy, and they have smaller intensity, because this gap is probably also smaller than that gap. That makes sense now?
Okay. The file.
No, I can open your figures, maybe it would be easy, or you remember how they look.
Oh, I don't know. This is how they look, and then this one is.
But this is for acidity.
Yeah.
I'm talking about propylamine, where we don't have problems, but I'm just explaining
Okay, got it.
why I like your propylamines and have no issues with that. Or maybe it was the device calculations, but I have issues with your acidity trial, right?
Yeah.
So does make sense now?
Yeah.
So
That
and
makes
this is what we call trap states, right? Because they're really localized, and these transitions are optically inactive or very, very weakly optically active. Plus, gap here is larger than this one, so you expect it to be red shifted, low energy, low intensity versus this ones, right? And
Yeah, just clicked, I got it.
this is we have, but I think I'm wrong. Well, it's not very big difference, but we compare this with that.
Yes.
But pretty much the same story. Now, when we go to these guys, on one hand you say, well, the gaps they look very much the same, are they? Well, again, you need
the
numbers, but
actual values,
roughly speaking, you have almost one. I would say they're kind of the same. Maybe this is a little bit larger.
That does look larger, yeah. Because this one's almost at, this is like 1.5, and that one's almost at 1. But they started.
But they're not larger by 1 electron volt, right? They're just by a little bit larger. Like even if this is, well, again, that's why values would be useful. But even if they're larger, they're probably larger by 0.2 electron volts, maybe 3 electron volts, right? It's not like 1 electron volt. Which means that, and again, we expect that your low transition should be optically inactive in both cases.
Yeah, and
So I
that's
did see
true.
the literature.
And
Like,
they're low,
Huh?
but the
The
problem
literature?
is that you have really almost,
I'm just kind of mad I
it's
didn't think of
probably
that
not like,
dual ligand
you
myself.
have almost 1 electron volt difference between
like,
this first
you can
transition
just
make sense.
optically
You can
low, right,
experimentally
and that transition.
purchase it in.
And this is what I don't
Mhm.
understand.
Yeah.
Why is there so much
Yeah.
blue shifted for
I'd already showed it to
silent?
Eric. He's like, well,
Looking
do
on
the
your
next time.
doors, I would say, well, you maybe, again, we need
Well,
numbers.
better than the
You said,
regular
like, it's a
setup.
little bit larger, which might explain something.
You do not
But
need
on
to
my,
match
from my
concentration.
perspective, they are just a little bit larger.
Yeah, not.
Not
Yeah.
1 electron volt
You do not need
difference,
too
right?
much
Yeah.
concentration,
Although,
so
check,
because,
I guess it's not 1 electron volt, but here they having really
right.
1 electron volt difference.
Yeah.
sweet
Also,
relief.
another thing is, this is showing your 3 electron volt transition, right? If you look on your gap, it's probably less than 3. think I really looked when I actually trying to measure, but again, it's not very accurate because of this.
Yeah, I'll have to get the actual.
But again, if this band gap is smaller than 3 electron volts, I mean smaller than whatever your transition here, and I think it's really close to 3 electron volts, this is where we have a problem, because in the case when we say, like, this picture is a single particle,
Karolinko's name.
you have no really electron-hole interaction, right? All electrons on the HOMA, I mean occupied states up to the HOMA, and you have nothing on the conduction band of the unoccupied states on that side, right? So there's no electron-hole interaction. When you do absorption spectra, you really excite. You take electron from the occupied state and you put it on the unoccupied state, creating a hole in a valence band, right? Because you really have a lot of electrons, and one is missing.
Washington, or is he?
Yes, a hole. And create an electron in the states where you have no one was there before, right? No carriers, and you put an electron there.
Yeah.
So you're creating this electron, and this is what we call hole. This is electron, right? This is how your orbitals look like.
You sent me one of his
Different if you
papers.
look on just
Still have to read
ground
it.
state orbitals, HOMA, and ground state orbital, UMA. So due to this, but we know that plus and minus, right? They interact through discharges.
Yeah, they are tracking.
Attracting, do you remember the formula? Well, at least the sign. Well, it's Q1 times Q2.
Oh yeah, I knew that.
Right, and because Q1 is plus and Q2 is
When I did
negative.
start plotting
we have
orbitals
minus. Well,
under
actually,
the symmetric
since it's
system,
electron and holes, they have
and
exactly the same charge. So
I don't know, those degenerate ones, they kind of
equals
vanish.
charge of the electron, and this is equals charge of the electron.
I probably plotted a range of
And then it's
at
4
least
pi
8 plus or
epsilon
minus,
naught
and there's only
and R would
one
be the
d orbital
distance
in the beta
between
Yes.
these charges,
that's
right?
unoccupied.
So, this is what actually we call Coulomb interaction. Because it has a negative charge, we said attractive, right? So wherever you have your energy for single electron, here's electron and hole, right? Here just, like as we said, in the ground state there is no holes, there's no this term there. You have this energy, and then you add this term to your Hamiltonian, which is minus, right?
Yeah.
And because it's minus, it should make it smaller. So that's why usually we have, this is your, we call it uncorrelated gap, means ground state band gap. And your first excited transitions, your optical gap among your first excited transitions is somewhere here, right? So this would be energy for your optical, those are the gaps. And how much is really smaller than your band gap, dictated by how big this interaction is. In quantum dots, we expect that this, because of the screen, right? And the dielectric constant increases if you have more and more electrons, because they screen each other.
Yeah.
They screen the positive charge of the nucleus, right? So in heavy elements such as cadmium, lead, even selenium, right? Those which you go to the bottom of the periodic table, the dielectric constant is higher because of the higher screening, comparing to carbon or hydrogen, for example. Hydrogen is a small constant. So, and if this is large, then the overall term is small, right? Divided by a big number. So that's why we're not expecting that this guide is very high, is very large for epsilon and epsilon 5 quantum dots.
But it does make it small.
But it has to be small, it cannot grow, right? So that's why I said it's important. Just looking on the first glance, I thought that this is smaller, less than 3 volts, comparing to your lowest transition. And this is what I said, I call looks strange.
Well,
And
I
that's
think-
why I
yeah.
was asking you to recalculate.
I think that before Levi left, that was the one we really like went over and did together. So that was why I was really
I mean, you
confused.
already recalculated?
Well, like when before he left, like I ran through and did the calculations with him, like watching like every step, making sure I was doing it right, and that was what I did it on.
But now, I would say, don't look on your files.
Yeah.
Look on that file from those, those one which you use for projected DOS. Of course, you need to take out the keywords for calculating the average.
Yeah,
academics.
yeah.
But you take exactly same geometry and use exactly same settings for your functional basis sets, right?
Yeah, I haven't changed any of the basis sets. I've over the past few
Well,
months,
but
I've
just
been learning
double
about
check
it.
it, I would say.
Yeah.
Be sure, 100% sure.
Yes.
And don't look on your structure
Right.
which
Right
you
now I'm
don't,
just
don't
still
look on the
looking at
files
cosine.
which you use for these calculations
Got
because we have them.
Yeah, because it's wrong. So
Start with a scratch, really use this as your
Got it.
initial thing and recalculate your TDDFT, right?
Yep. And then I'll.
And then let's see, if you will have exactly the same things, then you will start thinking. Because I think maybe there is some, maybe the structure was not those one which you think, or maybe something happened. Maybe it was not completely optimized.
I mean,
Possible. I don't know.
yeah, I guess it's possible.
If he was kind of showing it to you, maybe it was not 100% optimized and he decided, oh, whatever, just take the geometry and I will show how it works, right?
I have savings
Okay,
going,
good.
but
So looks, and mainly I was changing your captions. I don't know
Just
how
from
much
looking at the
it's
work, 'cause
easy to follow.
I mean,
my
I'll
my
ask
things.
you if I have any
Yeah,
questions.
but again,
But
the just kind of overall note, don't start that this image shows.
Oh, okay.
You just say natural transition, and we call it natural transition orbitals. Natural transition orbitals, right? Contributing to the, and then you can go with this one, right? So you don't, and you don't say, in the panel A we show, or something
Okay.
like that. You just say A, and it's a statement, right?
Yeah.
Because
I
this,
gotta
this
work on
saves,
it, not adding fluff.
it's a style, and you can see like this is all other things, figures which, especially those who are experienced students, graduate students,
Yeah.
have, right? So they have
Yes.
this different style because it saves spacing.
Mhm.
And again, we don't want to have figure taking half of the page.
Yeah. No, that makes sense.
So this is for you, and I have
All
your annotations here.
Doing
Our-
on Friday for this? What are we doing on Friday for this?
Which is
We
what you
will
do.
be having presentation, well,
For
we finished
Python.
presentation of John. I
Okay.
don't know when did you come, it was already finishing?
Yeah.
We
he
had very
was
bad
done.
connection, and that's why we have to stop. So we have John presentation and Levi presentation on his introduction,
Uh-huh.
and maybe if we will have time, we will finish those things which you didn't finish for other students.
Okay.
So
So I,
But I
I
think
don't need to have
Fridays-
this updated for Friday.
Oh, no,
Okay,
it's
I
for
was like,
next.
oh my gosh, I can't.
No. This is for next Tuesday.
Okay, so
And it's
the
a, like,
Tuesday after break then? Or next Tuesday?
Well, go on your schedule. I would say we probably can use a break to really wrap up everything,
Okay.
right?
Yeah, I mean, we'll see what I have going on, but I think I can at least try and get a decent amount done on that. These are for Austin and Lyndon, they're not here.
But figures really good.
Yeah.
If I look through the orbit,
Try.
Yeah, very nice. I mean, overall
Wingspan,
presentation
you
of
do
figures.
see
I
the
have
3D
really a
states
few things
that are
to
pretty
really
close in
figures,
energy.
right? I have very
Okay,
many
and then two that
Do you
things
Yeah,
for
but these are the two that-
for the
want to
comments.
rip this out for me, or?
No, it's okay because I have nothing done
Oh,
with
yours is
other
fine?
guys. I'm too slow. I don't know how Dimitri is able to do many of them at once.
Thanks.
Probably pay too much attention to details. as
Well, I
any
mean-
women has.
Probably.
And he's more like just going in general.
Is it somewhat
Picture.
recent? Yeah.
As it seemed to this group from computer, so
Oh, and the figure where you have bonds, right?
Uh-huh.
I was confused with completely confused with your notations because I didn't really figure out which one is which one, which bond is
Should I
which
put
one.
the little picture that I,
I think
have
you
back
need
in there?
not a picture, maybe the legend.
Okay, that sounds good.
And actually, the picture, the illustration of your network,
Uh-huh.
as you have in your poster,
Yeah.
would be useful, and you can use it. I mean, maybe we can do it as a separate figure.
Mhm.
Maybe you can add it to some other figures, like for example, where you have
You get extra
charge.
contributions.
Yeah.
Maybe you can show it because it's really small figure. You can add another panel
I guess that's a
for
personal
schematic
project.
representation of your
That
network.
has to be
Yeah, that's
carried
a good
out.
idea.
But this will be
Or the
easy for
people that
people to understand
approximate
what you're
or
talking
test.
about. I will give it to you.
Okay, sweet.
Thank you very much.
Yeah, I'll see you
So
on.
see you Thursday then, right? Are you having?
we submitted
It's your students which will. Oh, not here.
Oh, thank you so much.
Or maybe not for you. I don't know which students.
Austin and London, yes.
Yeah.
Yes, yes. I'll scan it at home.